So welcome to Math 150, Lecture 10, depending on how you're counting things. This lecture is on the method of least squares. This is one of my favorite topics in the course. Once you know this, you will actually know enough to be useful. You can actually work in the real world and solve things. There will be a contest between you and section 1. I need somebody who is responsible and a leader. All right. So if you guys win, everybody from section 2 is excused from 1 homework problem. As leader, you're excused from 2. Your vote will be the final vote in determining. All right. So here is a plot. What is the first thing that comes to your mind when you see this plot? Or what things come to your mind when you see this? Linear. Linear. Positive correlation. What else? Strongly correlated. What else? No units! Right? This is horrible. So if you've never read XKCD, it's a wonderful, wonderful series of comics. So for this one person goes to another, we should break up and I can prove it. I think we should give it another shot. And you see the plot of their relationship. Maybe you're right. I knew data would convince you. No, I think I can do better than someone who doesn't label her axes. And on XKCD, if you actually put your mouse and highlight over the strip, it gives you an additional comment. And the additional comment for this one is, and if you were to label your axes, I could tell you just how much better. You never want to have a plot without labels. So let's put labels. Force in newtons and displacement in meters. You might remember this as Hooke's law from physics. Force is proportional to distance. We're going to talk about linear regression, trying to find the best fit line. Most relations in the world are not linear. We will talk about how to deal with that. So I'm choosing my x's to be basically multiples, 5 plus 0.2n. And I'm guessing my relationship is y equals 5 times x. And I'm putting in some noise, some Gaussian error, just so it's not a perfect fit. If you look at this, does it look like the slope is approximately 5? When you look at this plot?
Yes.
Yeah, it looks like it's starting around 0, 0. And if you go up to x equals 20, it looks like it's around 100. So when x increases by 20, y increases by 100, it looks like it has a slope of 5. When you're covering such a large distance, and it's very linear like this, you have pretty much a good feeling, a good sense of that you got the slope approximately right. The intercept, however, is going to be much harder. And so when we do our calculation, we get a best fit line of 4.99x plus 0.48. So we see it's really close to the visual 5 that we thought, but the intercept, not so much. It's not horrible, it's not great. I often wear my Ohio State shirt when I give this lecture, but because there may be a school committee meeting, I'm not wearing it. Anybody know the full name of Ohio State? The Ohio State, actually, the Ohio State University, yes. So it's not A, it's the. For a lot of things in mathematics, there is more than one thing you can look at. Later today at 1 o'clock, I will be giving a lecture on extending the Pythagorean theorem and showing you multiple proofs. There's more than one way to calculate a best fit line, and different choices will give you different answers for the best fit parameters. This is similar to what we saw when we were looking at statistics for means, that you can have more than one notion of a mean. So our value of b is significantly off. If we use absolute values, we actually get 5.03 for the slope, and b is less than 10 to the negative 10 in absolute value. And so the difference comes from how we calculate our best fit lines, how we calculate our errors. So out of curiosity, how many of you have seen regression before? 1 or 2 people? 2.5, okay. How many of you have seen a proof of why it works? Okay, not as many as have seen it. So what I want to do is I want to talk about 3 notions of error. So let's say we believe y is linearly related to x. Maybe y equals ax plus b. So if I observe xi, I predict that y should be axi plus b. My first choice of error is just take the observed value yi and subtract what I predicted and then sum all the errors. The second is to take the absolute value, and the third is to take the square. So everything here, all of these slides are online, as well as the expanded paper that this is from. Amazingly, the notes I wrote on this when I was a postdoc at Brown are the most downloaded, cited article I think I've written in my entire professional career. Can anybody give me an issue with the first method? Observed minus predicted. Why might this be a bad notion of error?
Because it takes into account the negative values, and so like it'll positive and negative will.
Yeah, so imagine you have two data points. How many points determine a line? How many points determine a line? I know in some businesses, if you have one data point and your boss wants things to be going up, it's going up. And 1 point can determine a line. But in the mathematical world, how many points do you need to determine a line uniquely? 2. How many points do you need to determine a parabola? 3. ax squared plus bx plus c. If you have 3 points, you can solve for a, b, and c. If you have a cubic, you need 4 points. And there's formulas that allow you. So imagine I give you 2 data points. One is the bottom left, and the other is the top right. What do you think the best fit line is that connects them? So 2 data points, bottom left and top right. What will be your best fit line? Well, that's only if it's a perfect square. How would you find the best fit line? You would just yeah, so what would you do if I give you 2 points? Connect them, right? But if we use the first one, if instead of doing bottom left to top right, if I went from top left to bottom right, going in the opposite direction, the errors would perfectly cancel and there would be no error. It would be as good of a fit as going from bottom left to top right. This is absurd. So this eliminates 1. Can anybody tell me what might be good about absolute values or what might be good about squaring? These are 2 different ways you can measure errors. So you get rid of negatives. So that's something that's great for both of them. Neither one of them is going to have errors canceling. Why might you want absolute values or why might you want squares? So I know we don't always do this, but technically, what is the name of this class? Multivariable calculus. In fact, this is not just any old calculus class. This is the 3rd calculus class, which means you've taken at least 2 calculus classes. Maybe there's a calculus 0 that you've taken your pre-calc class. We've spent a lot of time teaching you calculus. It would be nice to be able to use it. What's the difference between the absolute value function and the square function? Does anybody know this in relation to calculus? So if you take y equals the absolute value of x, this function is differentiable everywhere except at x equals 0. Because as you approach it from 2 different sides, you get a slope of +1 one way and -1 the other way. The absolute value function is not differentiable. It means all of your calculus is not available. If you use squares, however, the squaring function is differentiable. This is why we use the method of least squares. This is why we measure errors by squaring things, because calculus is now available, and we will get a closed form expression using calculus in what other subject? Linear algebra. So calculus plus linear algebra will give us closed form expressions for the best fit values of A and B. The problem is because you're squaring it, 1 or 2 bad data points can have a huge impact on the best fit line. So if you have 1 or 2 bad observations, it's very sensitive. If you have 2 errors of 1, that's much worse than 1 error of 0 and 1 error of 2, because the error 2 is squared to 4 and contributes enormously. I like to phrase it, if I am being hired as the consultant, I like to use squaring, because I have a closed form expression. If I am hiring someone, I want them to use absolute values. And if you use absolute values, you have to resort to numerical exploration. So we will talk a little bit about this later. I'll go through the derivation, but this is a calculus problem, a multivariable calculus problem, hence the inclusion in today's lecture. How do I find maximum and minimum? Do I just find the partial derivatives and set them equal to 0? Is that all I need to do?
On the boundary?
Thank you. I have to find the boundary points. Now, let's think about what's going on here. As either A or B goes off to infinity, the error is going to go off to infinity. So I know I can't have my max or minimum at the boundary. I can't have my minimum at the boundary. The minimum error is going to be where the gradient is 0. DE3 dA, DE3 dB equals 0. What class ensures us that the minimum exists? So which class guarantees us that there will be a minimum? It's not linear algebra. It's real analysis. So real analysis tells us that the search will be fruitful. This is the George Carlin. I may have brought on board my grand piano, but I didn't, so I'm not going to look for it. He's going to look for the stuff he did bring on board the plane. Hopefully you will not be telling your children someday that you used to fly planes and travel around the world. You look for things that exist. Real analysis ensures us that there will be a choice of A and B that minimizes everything. And I'll show you how you actually calculate this. How many of you have seen 2x2 matrix equations like this? Okay, most of you please yell at your algebra teachers from high school, because the curriculum has changed a bit since I was young. All right, so let's go through the theory a little bit. So I'm pulling this from a handout that I've posted in a tremendous number of classes. So I have a function of two variables, but the two variables are not x and y. The two variables are a and b. So you have to remember a and b are the variables. Xi is the observation, the value I'm going to put in, and y is what I observe when I look at it at the value of xi. I want to find the values of a and b that minimize things. So I want to take the derivative of this with respect to a and b. I have a finite sum. The derivative of a finite sum is the sum of the derivatives. So when I take the derivative with respect to a or b, I can pass it through the sum. And I want to take the derivative of the square with respect to a. So if I take the derivative of the square with respect to a, the 2 comes down. I'll then get this whole expression to the first power, and I need to take the derivative of this with respect to a. What's the derivative of yi with respect to a? 0. Yi is a constant, it's an observation. What's the derivative of negative axi with respect to a? So the derivative of negative axi. What is the derivative of that with respect to a? I didn't hear what you said.
Negative A.
Not negative a, we're taking the derivative with respect to a. Negative xi. What's the derivative of b with respect to a? 0. And similarly, when we take the derivative with respect to b, we would just get now the derivative of negative axi with respect to b is 0. And what's the derivative of b with respect to b? It would just be 1. And so when we put this in, we want the gradient to be 0. So we want dE3 dA to be 0, dE3 dB to be 0. So these are the equations we get. And this is the algebra we just did a moment ago. So we set the two partial derivatives equal to 0. And we're now doing an optimization problem that has meaning. This is not a cookbook problem. This is not I just have to do something to fill up time. This actually is valuable and important. Well, since they're equal to 0, I can multiply everything by -1/2 and cancel the -2's. And so I just get this sum equals 0 and this sum equals 0. What are we trying to solve for? So what are we trying to find? A and B. So it's always worth remembering, what are you looking for? The x's and the y's are known. So if you think about what's going on here, I have a sum of yn times xn. That's just a number. I have the sum of a xn times xn. I can pull the a outside the sum. So think back to your Riemann sums. And it's going to be a times the sum of xn squared. I'll have the sum of b times xn. I can pull the b outside. And we can do similar stuff for the second equation. We have 2 equations and 2 unknowns. You can either solve it using substitution. First I write b in terms of a, plug that in, find a, and then plug that back in and find b. Or if you're comfortable with linear algebra, you can do some linear algebra. So when I pull things out, this is what I get. I get the sum of xn squared times a, the sum of xn times b equals the sum of x and yn. This is just doing the algebra. If you are having trouble with algebra, I strongly urge you to look through the handout and try to do this calculation and set it up. This is a good way to just review your algebra, similar to one of the problems we had on the last exam. And then imagine this is maybe 17, 10, 10. What would this last sum be? My sum little n goes from 1 to big N of 1. How much will that sum be? Not 1. It'll be capital N. I'm summing 1 capital N times. 1 plus 1 plus 1 plus 1 plus 1. So if the numbers are 17, 10, 10, maybe 30, I have 2 equations and 2 unknowns, and I can just solve for A and B. So this is just writing it in matrix form. If you've seen matrix form, this is very convenient. And linear algebra teaches you ways to automate this process. Well, this is of course, we did the same thing in calculus. How many of you have ever taken the derivative of x to the 24601? No one's ever taken, who knows what number 24601 is? Why do we care? Yes.
Like from Layman.
Yes, who?
Jean
Valjean, right? Prisoner 24601. So none of you have ever taken the derivative of x to the 24601. Are you going to have to write x plus h to the 24601 minus x to the 24601 divided by h, expand and take the limit? No, we automated this. We have a formula. The derivative of x to the n is n x to the n minus 1. Linear algebra allows us to automate a lot of this. And it's one of the things you'll learn when you take linear algebra. And so I'm not going to go through all the stuff here, but if you've seen matrices, you can pause on the slide. If you haven't seen matrices, ignore it. It turns out we talked about the determinant of a matrix. If the matrix is invertible, then you can always solve these equations. If the matrix is not invertible, it is unlikely but still possible that you can solve. And so we need the determinant of the matrix to be non-zero, and we get a closed form expression in the end. So when the dust settles, I'm going to skip the slide, we get our explicit formulas for A and B. And there's lots of different ways of writing them. I wrote them here using things like x bar for the mean. I can rewrite them the long way like this. Now, I have used George Carlin many times throughout the semester. I love his airline routine. I love this idea of looking for things that exist. There is the possibility that we might be dividing by 0. That'd be terrible. We need to make sure we don't divide by 0. Fortunately, there's only one way we could divide by 0. How many of you have ever done the physics experiment where you have an inclined plane and you have a ball rolling down and you want to see how does the time depend on the angle? What would be the stupidest thing you could do when you're gathering data if you want to see how the time depends on the angle? Don't change the angle, right? Keep the angle fixed at 30 degrees and get 1,000 data points. And now try to predict from that how the time depends on the angle. Should you trust any prediction on how the time depends on the angle if the angle never varies? If the angle never varies, all the xn's are the same, which means I can pull them out. It's the sum of 1 times that value squared. I could pull out those values. It's the sum of 1 times that value squared. The denominator will be 0. It turns out, it's a nice calculation, as long as at least 2 x's are different, the denominator will be non-zero and the method will work. So unless you do something truly stupid, like trying to see how things vary without varying the value, you will always get a value of A and B. All right, and so the formulas for A and B are reasonable. They can be seen by a unit analysis. I'm not going to go through this, but I'll just leave the slide for you to look at. You always want to have checks. Is my answer reasonable? All right, so to just recast this, if you haven't seen linear algebra, imagine I give you the equation 4 equals 3a plus 2b and 5 equals 2a plus 5b. And you might have stuff like this when I give you cookbook optimization problems. Well, one way to solve this is I could say 4 minus 3a divided by 2 is b, and then substitute for b here. Another way to solve it is I can multiply the top by 5 and the bottom by 2, and then I'll get 15a plus 10b, 4a plus 10b. So if I subtract, the b's cancel. I get a is equal to 10/11 when the dust settles. Now that I know a, I can substitute that in and find b. Why did I not write down what b is here? Because I don't care. This is just meant to show you how you can solve this without doing the linear algebra matrix form. But what you see is, well, there's an automated process I can do. As long as both of these coefficients are not 0, it tells me what to multiply and I can go through this. So why should I have to do this every single time? There should be a way, and that's what linear algebra will teach you how to do. so that you don't have to do this every single time. All right, some extensions. Most things in life are not linear. It turns out all that matters is it has to be linear in the unknown parameters, not in the inputs, not in the x's. So for instance, I could have a1 f1 of x plus a2 f2 of x all the way up to ak fk of x. We did the special case when k equals 2, f1 of x is just x, f2 of x is just 1. That gives you the best fit straight line. I could do the best fit cubic or quartic or quadratic. I could do sines and cosines. As long as it's the coefficients of the functions that are linear, I'm fine. What kind of matrix do you think this would be if I have k here rather than 2? Before we had a 2 by 2 matrix, this would be a k by k. And so it just becomes a slightly more involved linear algebra, but it's fundamentally the same type of mathematics. So as long as you're linear in the unknown parameters, you don't have to be linear in the inputs, in the xi's. So I know some people in the first class have been in a physics class where they were doing Newton's law of gravity, one of the greatest equations of all time. Yes, Einstein's theory of general relativity has subsumed this, but for all practical purposes, for the stuff we're doing on this planet, we can use Newton's law of gravity. So the force is proportional to some universal constant g, actually equals this universal constant g times the product of the masses divided by the square of the separation between the two. And you have a similar thing for charges. Imagine we wanted to guess that force was proportional to the radius to some power. Well, the problem is now because the unknown a is an exponent, it's not linear in that unknown parameter. You should have a Pavlovian response after taking a class with me that if you see a product, you take a logarithm. If you are teaching a third grader how to multiply, and say, okay, you want to multiply 3 and 4, take the log of 3 and the log of 4, add them, and then exponential. Okay, that's probably one of the only times you should not be doing a logarithm. But whenever you need to do algebra, if you have a product, it's often easy if you take logarithms. And so now if I take logarithms, I get the log of f is a log r plus little b. And there should have been a hint that I was going to do something like this because I have my exponent for the radius as a lowercase and my exponent for my constant an uppercase, because I'm not done yet. I'm going to be having a new constant. That new constant is little b is the log of big B. Notice we now have a linear relationship between the log of the force and the log of the distance between them. And now we can actually experimentally check if Newton's law of gravity is correct. As a nice heuristic as to why the exponent is -2, imagine you have force as some kind of yankage. So you have something in the center and it's yanking at everything. What is the surface area proportional to in terms of the radius? Surface area of a sphere is 4 pi. You should know 4 pi what? For the surface area. You should be able to get it just by thinking of units. What are the units of surface area? Unit squared, meter squared. So it should be 4 pi squared, right? So the surface area is growing like r squared. If force is decreasing like 1 over r squared, then if you look at a patch, the further out the patch is, the less it feels. But if you sum the contributions of all the patches, 4 pi r squared times 1 over r squared, that's constant. So the force is just being spread out further. So this is a nice heuristic as to why gravity in 3 dimensions might be out of the -2. It's really 1 less than the dimension. So here, populations from many years ago, 25 of the most populous cities in America. It often depends on how you define a city. Are you talking about the downtown, the metropolitan area, whatnot? And I can plot them. And if I plot them, it does not look linear. So I'm plotting the rank of the city versus its population. So this is the most populous, second most populous, third most populous, and so on. I can plot the rank versus the log of the population. It still doesn't look linear. But I can plot the log of the rank versus the log of the population, and now it actually does look pretty linear. And so this, I'm just doing it a little bit more in Excel, doing a log-log plot, you can see a straight line does a pretty good approximation. Do you think that there are people who are telling citizens where to live just so we can have this nice straight line fit? Probably not, at least not in a democracy. But a lot of phenomena seem to have these laws governing them. And when you do transformations of data, you can often sniff out these relationships. So whenever you have data, if it doesn't look linear, try doing a log or a log-log transformation. Take the log of just one of the inputs, take the log of the input and the output. And frequently you will get a nice straight line. Here is word counts. How often are certain words used? And again, depending on which method you're using, you will get different word counts. If you look at a work of Shakespeare, you'll probably see some words used frequently that are not used nowadays. Edgar Allan Poe would have a different distribution of words. An Arnold Schwarzenegger movie would have a different distribution of words, or maybe word. If you do a log-log plot, however, amazingly, you still get something that looks pretty linear. So I want to end with a few examples, and then we will have the competition versus section 1. So I already have their score. So I serve on a regional school committee. The following is a true real-world example. We needed to assign about $3.5 million in Chapter 70 funds to 3 schools: Williamstown Elementary, Lanesboro Elementary, and Mount Greylock. A couple of years ago, when I started serving, there were 3 school districts. Williamstown Elementary was one district, Lanesboro Elementary was one district, and the middle high school was another district that was shared by both towns. Amazingly, we actually had more school committees than buildings, because the 2 elementary schools had a super committee above them, which then worked with the middle high school committee to share some resources. So we were already, in some sense, partly regionalized. We were sharing a superintendent, we were coordinating some jobs and whatnot, but it made sense to fully regionalize. But we wanted to do it in such a way that each town still had control over their elementary school budgets. And so it was very important to know how much of the Chapter 70 funds, because 3.5 million out of 21 million, that's a sizable amount. We wanted to know how much money went to each building. Unfortunately, the Commonwealth of Massachusetts only tells you how much Chapter 70 funds goes to the district. It doesn't tell you how much goes to each individual school. And they keep their formula secret. So my goal was to figure out how to assign the money. So if we were to regionalize, we would save about $120,000. How should that $120,000 be shared between Williamstown and Lanesboro? Now, Williamstown has maybe twice as many students, maybe a little bit more, but Lanesboro maybe is not as economically developed. So how would you allocate the $120,000 between the 2 towns? I want an answer. How much should Williamstown get? What do you think is reasonable? There's a lot of answers that you can justify. I need a number.
According to previous allocations.
But we don't. But it's new because we have $120,000 in savings. We have $120,000 extra coming in. How much should go to Williamstown?
70 grand.
70 grand. So maybe Williamstown gets a little bit more than half because it's larger, but maybe not percentage-wise the 2/3 level. That's an extremely reasonable answer. The correct answer, according to the state, is of the $120,000, Williamstown gets negative $360,000, and Lanesboro gets $480,000. So I had to be very careful. I did not want a school committee vote on this because I did not think that this was a good allocation of $120,000. And so I said, let me try to sniff out the formula. And so I wanted a formula, and I can discuss this in greater detail if people are interested, a fair formula that did a good job predicting, it was transparent, and I could explain it to select boards, finance committees, and voters. And so I did a regression. And what I used for my inputs is I used the populations of the schools, and I used the property values of the 2 towns. And so I did my regression. I wanted my solution of the following properties. I wanted a solution to exist, the George Carlin. I wanted the values to be between 0 and 1. So I'm getting 3 numbers. What % of the money goes to each building? Unfortunately, the values are not always between 0 and 1, but you need something extreme for them not to be between 0 and 1. If 50% of the kids die in one town and 70% of the buildings burn down, then you will have some issues. However, if 50% of the kids are dead and 70% of the buildings have burned down, we have bigger problems than how do we allocate Chapter 70 funds from the Commonwealth. At this point, I don't think we're having money coming from the Commonwealth. This is the zombie apocalypse. This is the coronavirus out of control. Will the values be stable under small changes? If you just add one more person, is it going to wildly change how the allocation is done? And fortunately, the answer is it is extremely stable. Will the sum of the percentages add up to 1? It's actually slightly complicated math to prove that it will always add up to 1. It was fun proving that. I wish I could have explained this on the budget meetings, but nobody really wanted the proof. If it doesn't add up to 1, it's not a big deal. If it adds up to 98%, you just rescale everything. So that's not a huge deal. And so before we actually got the data back in 2018, I made my predictions. I forget which, so my prediction is the first column, the actual is the second, the difference. We're talking on the order of roughly about $10,000 per building. So this is in the level of noise. So the formula does a phenomenal job of predicting how to allocate $3.5 million. All right. So just, very quickly, many nonlinear relationships, as I've mentioned, are linear after you apply logarithms. So if I have, big Y is big B, X to the little a, and when I take logarithms, I get the log of big Y is a log of big X plus little b. So how many of you have seen Kepler's laws of planetary motion? All right, what's Kepler's first law?
Many years ago.
Anybody know Kepler's first? Yes.
Planets travel in elliptical.
Good, planets travel in elliptical orbits. Kepler's second, equal areas at equal time, how much you sweep out. And Kepler's third, this is the Sesame Street, one of these is not like the other. The square of the period is proportional to the cube of the length of the semi-major axis. And amazingly, Kepler got this from the experimental data he had on the orbits of planets. Now, whenever you see a constant labeled B tilde, this should be telling you I'm about to do some kind of operation to change things. So the square of the period is proportional to the cube of the semi-major axis. Let's just take the square root of both sides. And so I get the period is proportional to the length to the 1.5. So imagine we didn't know that. Imagine we wanted to just guess that there's some relationship, the period is proportional to the length to some power A. Well, the problem with this is A is an exponent, so I can't do linear regression unless I take logarithms. So if I take logarithms, I can now use linear regression. And so I have given you the data of the semi-major axis lengths of the planets. I have sadly stopped at Neptune, and I've given you their orbital periods. So when you look at this, I claim you should be able to tell me what B is. Anybody tell me what B is, approximately? Which planet do you think is the most special planet?
Earth.
Earth. What is the length of Earth's semi-major axis? 1. What was the very first thing we did today? Label. What units am I using? Astronomical units, Earth's distance. And the period, I'm measuring periods in years, and the period is about 1.0000174 for Earth. So what do you think B should be approximately? When L is 1, T is approximately 1, so B should be 1. And that's why I'm using these units. So there's some wonderful units. There's the Bruno, the Milli-Helen, the Slug, the Smoot. I will talk about one of them in a little bit. Here is the plot, and you'll be doing this for homework. It is a phenomenal fit. So even though you have Jupiter, which does have secondary forces, it's actually doing a phenomenal job predicting what goes on. Orbital deviations, even when they're very small, can be significant. This is how the planet Neptune was discovered. There was a disagreement between theory and observations for the orbit of Uranus, and they used this to figure out where Neptune was. And the person who did this was basically like the rock star of the 1800s. They didn't have traveling bands like we do now to predict the existence of a planet. The last one had been discovered in the 1700s. Before that, you have to go back to ancient Greece. When Uranus was discovered, it was one of the greatest examples of ass-kissing in the history of the world. The person who discovered it was British and wanted to name it after the King of Britain. The King of Britain loved this idea. The rest of Europe did not. But he was, I think, his efforts were appreciated by the king. So I will have you for homework actually do these 8 data points and see how great of a job it does in terms of predicting. Right. So this is one of the famous bridges into or out of Cambridge. We do not have fraternities on campus anymore. One of the things fraternities are famous for is interesting tasks for pledges. And this fraternity at MIT, I apologize for the resolution, they were wondering just how many of their pledge smoot would it take to go from one end of the bridge to the other. So they picked up smoot, marked, picked him up, marked, picked him up, marked, and went all the way down the bridge. And they got that the bridge is about 364.1 plus or minus an ear. I love the uncertainty. Cambridge did not find this amusing, and they had the marks painted over. The fraternity was upset. So what do you think they did? Did it again. And so this went back and forth until finally the city said, to hell with it. It's now been institutionalized. It's now part of the law of the region. They have smoot markers now on the bridge, and whenever there is a car accident, they report the accident as so many smoots. Now, one of the big things about me, if I have to use one word to describe myself, is opportunities. Whenever you can, you want to be able to distinguish yourself. You want to be able to shine. You want people to notice you. Years ago, I taught a winter study course on cryptography. And I had some pushback initially from parts of the college because I encrypted the title of the course. And I did the Caesar cipher. I shifted every letter forward by 3. And like, do you really want to have as the title of your course? Yes. It's going to be a conversational starter. And several of my students told me when they were applying for jobs, people said, I got to ask, what is this course you took? Does anybody know what happened to Smoot? You can't make this shit up. He became the chairman of the American National Standards Institute. And I'm just trying to imagine, well, I don't want to brag, but I am a unit of measurement. So what I want you to get out of the lecture that we've done up till now is the power of linear regression. Initially, people can only find straight lines. That's not so bad. But it only has to be linear in the unknown parameters. The functional form for your input, your xi's, that can be whatever you want. You can even have things that depend on more than one variable. That's fine. You can do multiple regression. We can take logarithms, and a lot of relationships that are initially not linear are now linear. I gave you just one example of work I've done with work I've done using this for the school district. I've done a lot of consulting with students. This is the level of what you need to be useful. How many of you know the birthday problem? How many people do you need to have in a room before you have at least a 50% chance? Around 22, 23 is roughly what you need to have a 50-50 chance of 2 people sharing a birthday. Section 1, we actually have a pair of twins, so it's really not that challenging to have that here. Here, based on the numbers, there's a chance that I would have it, but it's not, I'm not overly optimistic, so I will wait and not do that today. But what you can do is you can actually try to figure out theoretically what is the probability. And in fact, you can do it assuming that there are d days in the year, and you get that the answer is approximately the square root of d times the square root of log of 4. That's about how many people you need if there are d days in a year to have a 50-50 chance of 2 people sharing a birthday. And so I just did some plots. And I did 2 different simulations of 10,000 simulations with d chosen from 10,000 to 100,000. Calculated the best fit lines. I took logarithms, and I got, in the first case, 0.506 for A, for the second, 0.481. So pretty close to a half. It's sniffing out that exponent. And again, as before, it's having trouble with the intercept. All right. So this finishes the main part of the lecture. It is now time for the